Hi everyone, my name is Katie and I've been doing some research here at UCSD with a fairly recent nanomaterial known as aerogel. And for those of you who don't know, it is holographic blue in color. It's super light and it has a lot of applications that are currently being developed. And so today, to learn more, I have 3 interviews set up for everyone. We'll be interviewing chemist Ian, NASA engineer Katie, and also scientist and researcher Erin to learn more about what aerogel is and all of its applications and the future use of it as well.
Hi, I'm Ian, professional chemist and gelatin-based snack enjoyer, and today I will be explaining the process of creating an aerogel. All aerogels start out as a normal gel, which is then put into a pure solvent for a long period of time to ensure all the impurities are removed from the gel. After this first step, we are left with the gel containing a very pure liquid inside of it, and the question of how do we remove that liquid from the gel. Normal drying won't work for making aerogels. This is because of a phenomenon called capillary action. This capillary action is the reason why meniscus lines appear when you pour a liquid into a beaker, as the liquid sticks to the beaker's walls and pulls itself up. In the context of gels, however, this liquid sticks to the framework of the gel, and as it evaporates, it pulls on and collapses the gel's framework. We have to avoid this capillary action in order to create an aerogel, and this is done through a process called supercritical drying. To understand supercritical drying, we must first look at a phase change diagram. As you can see, the phase of an object depends both on the temperature and the pressure on it. Gases and liquids are closely related and can switch between each other through evaporation and condensation until a critical point is reached. After this critical point, the object becomes what is called a supercritical fluid, where the gas and liquid phases are no longer distinguishable from each other. This is important because a supercritical fluid does not have capillary action and therefore won't collapse the gel when it's removed. By using this property, if we carefully control the temperature and the pressure of the gel, we can slowly remove the solvent when it is in this supercritical state, until enough of the solvent is removed that when the solvent cools down, it'll cool directly into the gas phase instead of the liquid phase. After this process, we are left with an aerogel. Now that you know how aerogels are made, I will be passing it on to our NASA engineer, Katie. Thank you for having me.
Hi UCSD, thanks for having me here today. My name is also Katie and I am a NASA engineer, but I work specifically with the Jet Propulsion Laboratory known as JPL in Pasadena, California. And in 2004, I worked on a mission known as the Stardust mission. And you may be wondering what this has to do with aerogel. As you may know, aerogel is a great insulator and it's used in many things from cryo blankets and pyro blankets to clothing, but it's also been used in NASA missions that have gone interstellar. So in the Stardust mission in 2004 that I worked on, we used aerogel to collect comet dust and interstellar dust. And aerogel was a great thing to use because it was so lightweight, and because of the density of the material, it didn't cause any harm to the particles that we were collecting and that we later used to study space and things of that nature. So this here is a typical picture of aerogel, and it's super interesting, that holographic blue color, and you might look at this and think, well, what does it have to do with space? So this is the press kit released in 1999 from NASA from the Stardust mission that eventually happened in 2004. And within this big machine whose sole purpose was collecting interstellar dust, there was this aerogel component that was used to actually collect the comet dust and the stardust. So just a really interesting application of aerogel that I was excited to share with you guys today. I hope you all learned a little something. And on to our next speaker, researcher and scientist, Erin. Thank you.
That was very interesting, Katie. Now I'm going to talk about why it's not widely commercialized yet. Aerogels are interesting for a variety of applications due to a number of their characteristics, yet they are not widely commercialized for a number of reasons. First, its high cost. The expense of manufacturing aerogels on a big scale keeps them from being as appealing for commercial application. Next, complex production processes. Aerogel manufacturing requires for specific equipment and condition, making it challenging to scale up production. Lastly, lack of durability. Several aerogel varieties are fragile and easily destroyed, which restricts their usage in some applications. So, how do we solve these problems? Works on a continuous process and recovered feedstocks are two areas where improvements are still being made to optimize the supercritical process and lower related expenses. Alternative methods, including ambient pressure drying, freeze drying, and even 3D printing, are still being developed. Utilizing silica aerogels with other composite materials or employing other cross-linkers to create hybrid components with various structural properties involves a number of stages. Separately, polymer aerogels such as polyureas, polyurethanes, polyamides, etc. are being developed, and they exhibit good mechanical performance when formed into monolithic panels for thin films. The field of aerogels will continue to grow quickly in the years to come. Today's architects are deeply involved in a discussion about sustainable energy, oil costs, the energy crisis, etc. They are now more conscious of how their structures affect the environment. They strive to develop structures that are environmentally friendly in addition to having a good design. Aerogels are a cutting-edge substance that satisfies each of these criteria. Due to its superior thermal conductivity and luminal transmittance, silica aerogels provide a substitute for conventional insulation. The methods to make it much harder, lower, and less dangerous are being looked into by researchers. That's all we've got for today, and thanks for watching. We hope you find it informative today.